Hello, in this lesson, we're going to talk about one-sided limit and when do we use it and how. First of all, we have covered so many concepts, right? The intuitive definition of limits and what it means for limit exist in relationship with one-sided limit. As long as, the many limit laws and the direct substitution property. And we are now looking at a one-sided limit. When is one-sided limit necessary? Well, you have to see the situation. For example, okay, so we're going to take the first one, for example. We are interested in the limit of an absolute value function when x is approaching 0. And this function, absolute value function, we know that it will turn out to be a piecewise function as x is approaching, if x is greater than or equal to 0, right? So we're going to write these two piecewise function. If x is positive, right? If x is positive or 0, the absolute value of the number is going to be the same. If the input is negative, input x is negative, the absolute value of x is the opposite. We understand that. In this case, we will have to use one-sided limit. So when x is approaching 0 from larger than 0, okay, and then because x is approaching 0 from larger than 0, x will be assumed positive, right? Because x approaching 0 from the larger side. So we will apply this rule. So this absolute value of x will turn to positive is equals to x. And then direct substitution equals to 0. If x is approaching 0 from smaller than 0, right? So this is a negative sign on the shoulder. The second rule would apply. The second rule would apply, so we get the absolute value of x of a negative number, which is, this is going to be a negative sign, smaller than 0, x is negative, so the absolute value of x is opposite. And now direct substitution, we got 0 as well. And according to this theorem, the limit from left and limit from right are the same. Therefore, this limit, when x is approaching 0, the absolute value of x, when x is approaching 0, is 0. Okay, so you can say thus. Okay, sometimes we can use these, we can use the notation such as because. Okay, I'm going to show you a couple of mathematical notation, shorthand mathematical notation. Because, let's see if I can find them. It's a 3 dots upside down. Bring my glasses. There we go. No, actually, I don't find it for the moment. So never mind. Okay, you can use the word because or therefore. Okay, all right. So let's look at the second example. The second example, it gets a little bit more complicated. And we're still going to use this piecewise function, which is the alternate to represent the absolute value of x. When we consider this limit, we will have to consider when x is approaching 0 from larger. And we also have to consider the limit of the function from smaller than 0. So when x is approaching 0 from larger, because x is positive or 0, well, by the way, right? There's a little details I need to mention. Okay, first we need to notice the domain of this function is x cannot be 0 because we have a denominator in the we have an x in the denominator, so x cannot be 0. So when we apply this property, it actually x is not going to be 0. X is not going to be 0 under the circumstances. So when x is approaching 0 from larger than 0, we are doing that in the domain of the function. So x is positive. Well, x is positive, the absolute value of x is the same as x and equals to x over x, because x is not 0, therefore we can reduce it to 1. And the limit of 1 equals to 1, right? Limit law. And in the second case, when x is approaching 0 from smaller than 0, when x is negative, the absolute value of x is its opposite over x. And this time we also can reduce because x is approaching 0 from smaller than 0, but it is not 0. So this will be -1. The limit of -1 is -1. And since the limit of the function, the limit of the function from left is not the same. It's not the same as the limit from right, right? So according to this property, okay, I'm going to bring it down here. And thus, you can say therefore, right? You can say, also you can say because this is not the same, 1 is not equals to -1, and therefore this limit, oh wait, sorry. So this limit does not exist. So this limit does not exist. Done. Okay, you can see in these two cases, we need to use one-sided limit. One-sided limit. Now, another situation, we have to use one-sided limit. Take an example for this one, okay? We're not gonna look at the picture, right? So because sometimes you may think, okay, we have to graph this. You don't have to. Let's do one without the graph. Okay, I will show you the graph later. So in this case, if we have this, we obviously see there's the three rules. The three rules depending on where x is, right? Where the input is. So we're gonna you can easily draw a number line, and the point where we have questionable is 0, and the other point is pi. Right, so these are the two numbers. These are the two numbers. And less than 0, right? The rule is 1 plus sine x. So that's the rule for x less than 0. Between 0 and pi, the rule is cosine x. And you have to mind the interval, right? Less greater than equal to 0, less than pi, right? So you want to attach these conditions for our convenience, right? So you want to attach these conditions for our convenience, but this is like a little more, it's a little picture that could maybe help us to identify, right? So it's another way to read this, the given situation. And the last one, the rule is sine x, right? Sine x. So on this rule is for x greater than or equals to pi. So including pi. Including pi. So isn't just another way to look at it. You don't have to do this, but if it helps, right? I think this will probably replace the picture to a certain extent. Okay, replace the picture to a certain extent. That's what we want. Now, what we are interested in is the first of all, suppose I'm interested in the limit. I'm interested in the limit as x approaching 0, f of x. Well, the rule of the function changes before and after 0. So this will be the situation, is to observe this limit. We're going to have to observe the function's behavior in the limit state when x is approaching 0 from smaller than 0, and also from larger than 0. So this naturally, you can see we will need to do one-sided limit. We need to do one-sided limit. So let's keep going. Okay, so when x is approaching 0 from smaller than 0, for smaller than 0, our rule is 1 plus sine x. So you just replace f of x by 1 plus sine x. And this is going to be a direct substitution, right? So it's going to be sine 0. Sine 0 is 0, so in the end we get 1. The next one is when x is approaching 0 from larger than 0. And the rule is a different rule now. It's cosine x. Cosine x. So cosine x is in place of f of x, because when x is approaching 0 from larger than 0, we use the rule for cosine x. And then we can directly substitute, and that equals to cosine 0. Cosine 0 is equals to 1. So now the limit from left of 0 is the same as the limit from the right when x is approaching 0 from right. Right? Since this is true, okay? So according to that theorem that we have used here, right? This is very useful tool, right? Then, since this is the reason, and therefore this limit, not only it exists, it is equals to 1. It is equals to 1. Right? So this is how we work this. So in this case, we have a limit. So let's observe another limit. And this time we're going to observe the limit when x is approaching pi. Okay. When x is approaching pi, of course, we're going to have to do it left and right again, right? So on the left, when x is approaching pi from smaller than pi, versus when x is approaching pi from larger than pi, we have different rules. So very similarly, we're going to apply the rule when x approaching pi from smaller than pi, and that's the rule which is cosine x. Okay, and direct substitution, cosine pi equals to -1. And the other one, when we apply the rule, when x is larger than pi, the rule is sine x. So sine x replaces f of x. So direct substitution is a sine of pi. Sine of pi is 0. So by this time, we have seen that these two limits from left and right, from left of pi and from right of pi, are not the same. And so we apply that we apply that since, right? So we apply that property one more time, and we draw the conclusion that the interested limit does not exist. That's it. That's it, right? But you can see the necessity of using sighted limit. Now, for those of you who can draw the picture, who like to see the picture, you can either do the picture which will help us to see better, right? So you can see from the picture, which confirms our observation. But having the picture is not absolutely necessary. It's not absolutely necessary if we have the rules explicitly given. Okay, so the picture obviously reflected when x is approaching 0, right? When x is approaching 0, then from left and right, the limit are the same, which is 1. But when we're approaching pi from left and right, the limit are different. Oops, sorry, get this, right? So the limit are different. So at a 0, limit exists, and at pi, limit does not exist. Okay, so what tool do we use? What is the theoretical the theoretical basis for that is that we apply this theorem. Okay, we apply this theorem. All right, so let's keep going. Example number 4. There are situations that we're given a function, but by observing the function, we have to use one-sided limit. For example, we have number 4. I'm going to clean this up. Look at this situation. When x is approaching 4, when x is approaching -4, it could be approaching -4 from left or right. So this function, the rule could be different, right? Because if x plus 4 is larger than 0, right? So we'll have two cases. So if x plus 4 is greater than or equal to 0, meaning x plus 4 is positive or 0, then the absolute value of x plus 4 is going to be the same. But if x plus 4 is negative, then the absolute value of x plus 4 is going to be its opposite, x plus 4. For this reason, we're going to have to, in order to know whether this limit exists, we're going to have to look at the limit from left. And we also have to look at the limit from right. So in both cases, we're going to have to deal with the cases respectively. When x is approaching, let's continue. Okay, let's continue this, right? When x is approaching 4, right? So we continue this. On the right-hand side, if x plus 4 is greater than or equal to 0, that means if you subtract 4 on both sides, that means x is larger than or equal to -4. If x plus 4 is less than 0, that means x is less than -4. Excuse me. Okay. You can also use number line to help us to identify the rule change at -4. When x is less than -4, the rule is, this is the rule. Excuse me. And the number line to the left is less than -4. Larger than -4 or equal to -4, the rule has changed to x plus 4. Okay, so these are the tools. You don't have to necessarily show it, but I'm showing you here just to give you an example. You can also do the graph for x plus 4, okay? So that if that helps, okay? All right, so now we're coming back to evaluate this limit, Now, when x is less than, when x is approaching -4 from smaller, that means x is approaching -4 from smaller than -4. So we're using this tool, we're using this rule to replace the absolute value of x plus 4. So this rule is going to be replaced by the rule which is like this. Okay, so we can put a bracket to make it nicer. And then once we drop the absolute value sign, we're going to organize the term inside. So that's minus x minus 4, right? Minus x minus 4. So now we can do direct substitution because this is a polynomial. This is a polynomial. So we get a negative 3x, right? Negative 3x. And direct substitution, we will get negative 3x minus 4, replace x by negative 4 because this is direct substitution. In the end, we get 12 minus 4, that's equals to 8. Okay. Excuse me. And then let's look at if the limit is done from the right. When x is approaching -4 from larger than -4. And this time, x, the absolute value of x plus 4 will be replaced by the other rule. And in this case, once again, we get to a polynomial. And we have combining like terms is a 4 minus x. And direct substitution, we got a 4 minus x is replaced by -4. And we get 8 again. We get 8 again. All right. So we observe a limit from left and right, and they are the same number. Okay. So once again, since these two are equal, then we can say that the interested limit is going to be equals to 8. Okay. Next one. Number 5. Number 5, we have a similar situation, right? We have to observe the limit from left and right, and we can borrow these work we've done there, right? So we can borrow these work we've done there, right? So observing the limit from left and right, smaller than 4. So we put a shoulder on the left. We put a positive sign, negative sign on the shoulder. And now when x is approaching -4 from smaller than -4, absolute value of x plus 4 will be replaced by the rule in another form. Then you say, why do you have to do that? Well, if we don't drop the absolute value sign, there's very little we can do. Okay, there's very little we can do algebraically. So now continue. You might notice that the denominator can be factored, right? 2 can be factored out. So that will become 2 times x plus 4. X plus 4 and x plus 4 will be reduced. So in the end, we get the limit as x approaching -4 from smaller than -4, which is going to be negative half. Okay, it's negative half. So the final limit is negative half. On the other one, similar, right? You can see we use the factoring technique. This time when x is approaching -4 from larger, so this other rule will be used. So x, the absolute value of x plus 4 is replaced, and 2 times x plus 8, and we factor it, we get 2 times x plus the same, right? And this time, obviously, you see we're gonna get a positive 1/2. Negative half and positive half are not the same. And therefore, you can see applying that theorem one more time that the limit does not exist. So limit from left and limit from right. So this is how you say it, okay? How you express and show your work, okay? Then, right, we say this limit does not exist. Does not exist. Now let's look at number 6. Number 6. Number 6 on the first side, it looks a little, it looks like we need some work. But we are only interested in the one side limit, right? We are approaching half from smaller than half. So first of all, let's see if it looks like we can do some factoring, right? It looks like we can do some factoring in the denominator. So in the denominator, we can factor out the x squared. So that becomes 2x minus 1. 2x minus 1. When we take the absolute value, right? When we take the absolute value, a times b, it is equal to, we can take absolute value of a multiply the absolute value of b. And for division, it's the same. So if we take absolute value of a quotient, okay, a divided by b equals to the absolute value of a divided by the absolute value of b. However, okay, so however, if you have absolute value of a plus b, and that is not, this would not be true, okay? So this would not be true. So you cannot use this latter one. Okay, that's why it's so restrictive. Whether you have plus or minus, this is not going to work. Okay, so it's because they're not equal. They're not equal. If you have any questions about it, ask me, ask me. Now we're gonna move forward. I'm gonna use this property on the top and bottom, but x squared itself is a positive, right? So we obviously from this process, we recognize the domain. What is a domain? Domain is that denominator cannot be 0. So this piece, right, to determine domain, it cannot be 0. It cannot be 0. So in the domain determination, right? So we know that 2x minus 1 cannot be 0, right? In order for that product not equal to 0, and x squared cannot be 0 either. Okay, to guarantee that product is not 0, so these two cannot be 0. So end. All right. So of course here x cannot be equal to half. So x cannot equals to half. And the other one is, of course, x cannot be 0. Okay. So with all of these we're doing here, it's always in the domain. So we need to be aware of the domain. So that's the domain. Okay. Sometimes the domain is not asked of us directly, but it is always implied. All the operations about function is done in the domain. Okay. So put this on the side because these are just a review and you don't need to show these work. All right, so now we're going to apply the product in the denominator. So what we get here is that we're going to, because we know x is not 0, and we're going to take the absolute value like this. Okay, and we take absolute value for x squared. But x squared itself is positive, right? Wait. Okay, so this is x squared. X squared itself is positive because x cannot be 0. Therefore, the absolute value sign can be dropped. You see what I did there? You don't need to wrap x squared with absolute value sign because it's positive already, right? But now we have a scenario that we have x is approaching half from smaller than half. I mean, what do we do? Then we can do the following. Since, okay, you can do something like this. You can, but you don't have to. Okay, you don't have to. I'm going to show you another way to do it. Since x, we're going to use the situation. We're putting into the situation where x is approaching half from smaller than half. What does that mean? Right? Because x is approaching half from smaller than half, that means x is smaller than half. If x is smaller than half, if we multiply both sides of the inequality by 2, so that means 2x is less than 1. If 2x is less than 1, that means 2x minus 1 is less than 0. Right? So you can see from that setting we are in, x is approaching 0.5 from smaller than 0.5, which is less than half. That implies 2x less than 1. We multiply on both sides by 2. And we subtract 1 on both sides. So 2x minus 1 is less than 0. What does that tell us? This tells us that 2x minus 1 is negative. If 2x minus 1 is negative, the absolute value of it is its opposite. Okay? The absolute value of it is opposite. So that's what we want. That's what we want. So by the time we get this, and then let's finish this question, okay? So we get it here. So now we can substitute the absolute value of 2x minus 1 by its equal under the circumstances. And now we can reduce 2x minus 1, 2x minus 1, because x is approaching half from smaller than half, but it is not equal to half. The intuitive definition of limits. So after that reduction, what do we have? Right? We have a negative sign, and this is gone. right? So this is gone. And we can put our negative sign in the front, right? We have a negative sign there, so we need to keep that negative sign. 2x minus 1, 2x minus 1 reduced. So we get negative of 1 over x squared. Now what do? It's a rational function. We can directly substitute. So we're going to directly substitute x by 0.5. And that's squared. And in the end, of course, we get -4. Okay? Now, so this is how we handled in order to release the absolute value sign from the absolute value of 2x minus 1 under the circumstances. So by this time, the question is done. But if you have any issues that you have hard time with it, I want you to take another look. Okay, we're gonna do it similarly as we did it here. Okay, so alternatively, to handle 2x minus 1 in absolute value, we can do what we did similar to absolute value of x plus 4. And how do we do that? And this is what we can do. Okay, we know that if 2x plus 1 is greater than 0, right? We know that, or greater than equal to 0. Then if 2x plus 1 is greater than equal to 0, the absolute value of 2x minus 1 is going to be the same. If 2x minus 1 is less than 0, excuse me, is less than 0, the absolute value of 2x minus 1 is going to be its opposite. 2x minus 1. And go one more step, right? So we're going to solve the inequality. We keep these things here, right? And solving this inequality, what you do? You add a 1 on both sides, you divide both sides by 2. So you're going to get x is larger than half, or x is less than half. So for x is less than half, that's the situation we are in. So we got these two, but we don't really need this first branch. We only just need the second branch because that's the situation we're in. And then you can still continue to do from this step, right? Well, x is approaching half from smaller than, so you still substitute absolute value 2x minus 1 by negative of 2x minus 1. So you get the same conclusion. So either way, we need to handle these absolute value situation and work with sided limits. And this is just one-sided limit. So let's see the next one. Next one is the last one, okay, for this episode. Excuse me. All right. We're interested in when x is approaching 0. Obviously, if you consider the domain is x cannot be 0. Pretty straightforward. Here. X cannot be 0. However, we have absolute value of x here. So we have to consider the limit from left and limit from right. And of course, we also know that the absolute value of x is has two branches. Okay, So we're gonna borrow from what we did earlier. Like, let me just make a quick trip to earlier work. Okay, gonna put it on the side. By this time, you're pretty familiar with it, but if you're not, we still have it around. So let's do this one at a time. Right? So we need to find these two limits. We need to find these two limits. So this time I'm going to change the way to write it. Okay, I'm writing it vertically, which is a lot of people favor that. So when x is approaching 0 from smaller than 0, the absolute value of x is its opposite. So the absolute value of x will be replaced by its equal under the circumstances, right? Which is x approaching 0, smaller than 0, imply x is negative. Now, what do we have here? Right? 1 over x minus 1 over negative x. So that's going to be 1 over x plus 1 over x. Right? So this is going to be a plus. And then we ended up with 2 over x. 2 over x. Okay? And x is approaching 0 from smaller than 0. Right? This might remind us of because 1 over x, 2 over x, they're very similar picture. And what would this be approaching? This is going to be approaching negative infinity. Okay, negative infinity. We can refer to the picture we did before, this picture. The only difference between these, the only thing is that in this case, it's 2 over x. But what we look at which branch? We're looking at this piece, right? Because x is approaching 0, but of course, oh, that's 1 over x. I can just change it 2 over x. It would be this similar picture. Okay, this is just a scale a little bit. So when x is approaching 0 in our situation, right? X is approaching 0 from smaller than 0, and you can see the output approaches negative infinity. So that's how we get negative infinity. Okay. All right. So let's clean this up. Let's look at the next one. Let's look at the other side of the limit. Right? If x is approaching 0 from greater than 0, what do we get? Well, in this case, the absolute value of x is the same as x because we're applying this property. And now 1 over x minus 1 over x, what does that equal to? It equals to 0, yes. So the final limit is 0. And obviously the intended limit we're interested in does not exist. This limit does not exist. But this limit exists, right? This limit exists. This limit exists equal to 0. And that other one is a negative infinity limit. Well, it's not a limit, right? So these are the examples. Summarize, as we can see these examples, in some situation, we're given a function that we have to do one-sided limit. And because the rules are different, So you're going to see a variety of these examples. And there'll be in another video, right? You can see whether, sometimes you don't need to do one-sided limits. Okay. So usually when we do one-sided limit is usually because we have to. Okay. If we don't have to do it, then we don't do it. All right. Thank you for watching.